trigger finger for Her Majesty. Another one with the golden tongue, poison in your veins.
Here we have some current flowing in this conductor, and of course it produces a magnetic field, and we are supposed to calculate its effect on this current loop that also has same current running through it. So if this is I here going this direction, then it will produce a magnetic field into the screen everywhere where this loop is. And let's evaluate the direction of these forces on each side. So over here, the current is also going to the right, so we point our right hand fingers over that direction and then curl our fingers into the screen, which means here's F1 force upwards here. And we can say that already because these two currents are parallel, that it will be an attractive force, so it has to be that way. On the other hand, the direction at the bottom is the reverse, so there's going to be force downwards. So this one and this one are repelling each other because the currents are in opposite direction. Although the side connectors or side conductors are perpendicular to this wire, it doesn't mean that there wouldn't be any force. So the current is going in this direction here. So L cross B in that case would mean that there's a force in that direction, F3. And the opposite is true in this case. L cross B gives a force to the right. But because these conductors are of same length and they're equally far from this conductor, at every point these two forces cancel each other, so the net force of F3 and F4 is 0, so we don't have to worry about them. We only have to be concerned what is the net force of F1 and F2. As always, the general expression of a force between two different wires, or magnitude of the force between two different conductors, is μ0 divided by 2 pi r times the current in the first conductor I1, and if we call this one I2 and this one I3, well, the current is the same in all of them, so we don't even need these sub indices here. So I1 and then the current in this one or the other conductor, another I, and then the length of the conductor where the force is acting. So okay, let's put these indices here anyway just for clarity. So 2 refers to the target conductor and 1 is the one that produces the field. So in this case, for F1 we get μ0 divided by 2 pi r1, where r1 is this distance, 3 centimeters, and then I1 is just I, I2 is just I, so that's I squared, and then L2 is the length of this one, so let's call this L, so that's our L. And F2, similar fashion, μ0 2 pi R2, which is now 5 plus 3, 8 centimeters. same thing, I squared times L. Well, let's define our positive direction to be upward. So in that case, F total F1 minus F2 and we'll get mu0 2 pi. They also have the I squared term and L in common, plus 1 over R1 minus 1 over R2. And plugging in the numbers, mu0 4 pi times 10 to the minus 7 Tesla meters per ampere divided by 2 pi, and the current is 3.5 amps squared, and the length here is 0.1 meter. And then these terms, 1 over R1 3 centimeters, and R2 8 centimeters. That gives us 5.1 times 10 to the minus 6 newtons. And because this is positive, the net force is upwards, which makes sense. The current is the same both here and here, but because this one is closer, the attractive force must be larger than the repulsive force.
Tricky little gun, giving silence to the one that'll never see the sunshine. Another inch of your life sacrifice.